Hello, welcome to Basics of Finite Element Analysis. This is the third week of this course and today is the third day. Yesterday we were developing or we had developed an expression for creating approximation functions of nth order in the natural coordinate system, and this is the expression we had generated. So, the power of this expression is that we can generate very easily any order approximation functions using this relation, and it can be very easily computed. What we will do today in the first part is actually develop some of these approximation functions in natural coordinate system for two different values of n, so that you get a little bit of practice of how to use these functions in terms of how to use this relation and generate approximation functions. So, what we will do is, the first thing we will do is we will generate approximation functions when n is equal to 2. So, this means that the approximation function will be linear, it will be linear in nature. So, you have the zeta coordinate system and its first node is located at -1 and the second node is located at +1, and it has only two nodes, node 1 and node 2. There is no intermediate node. So, we have to generate psi 1 as a function of zeta and psi 2 as a function of zeta. This is what we have to generate. So, psi 1 zeta equals, right. So, what is the value of I in this case? 1. So, if it is I is equal to 1, and how many, if I is equal to 1, then I will not have psi 1 in minus psi 1, right, because the value of psi 1 at first node is going to be 1. So, I will not have psi 1 minus psi 1 term. So, that will not be there. So, I will have psi minus psi 2, right, psi minus psi 2, and will I have psi minus psi 3, psi minus psi 4 and all that? I will not have, right, because this index will only go up to 2, okay. And in the denominator again I will not have psi 1 minus psi 1, but I will have psi 1 minus xi 2, or zeta, I am sorry, zeta 1 minus zeta 2, and in denominator I will have zeta 1 minus zeta 2, okay. So, if I simplify, I get, so denominator zeta 1 minus zeta 2 is minus 2, right. So, that is my denominator into zeta minus zeta 2. And let us look at its values. At zeta equals minus 1, at zeta equals minus 1, what is the value of this? You please calculate, it will be 1. Minus 1 minus zeta 2 is plus 1. So, minus 1 is equal to minus 2, minus 2 into minus 1 is 2, 2 divided by 2 is 1. So, this is at its value is 1 at zeta equals minus 1, and at zeta equals plus 1 its value is 0. Okay. Let us look at psi 2. psi 2 as a function of zeta is equal to, so from equation C, what is the first term we will have in it? Zeta minus zeta 1, and we will not have zeta minus zeta 2, because when zeta becomes zeta 2, then this will become 0. So, we do not have that term, and then divided by zeta 2 minus zeta 1, and in the denominator, so the denominator is 2 and the numerator is zeta minus zeta 1. And let us look at its values again. Its value is 0 at zeta equals minus 1 and 1 at zeta equals plus 1. Okay. We will do another example and then we will move on. So, this was for n equals 2, now we will do n equals 3. So, if it is n equals 3, then we have what kind of approximation functions we will have? It will have, we will have quadratic approximation functions. The nodes will be at 1, minus 1 and 0, right. This is node number 1, this is node number 2, this is node number 3, and we are interested in finding out psi 1, psi 2 and psi 3. So, let us write an expression for psi 1. Psi 1 as a function of zeta equals, so I have, this corresponds to the first node. So, I will not have psi 1 minus psi 1 term here, right, and I will have, so the first term will be zeta 1 minus zeta 2, and the second term will be zeta 1 minus zeta 3, right, and in the denominator I will have, oh I am sorry, zeta minus zeta 2, yes. So, in the numerator the first term will be zeta minus zeta 2 and second term zeta minus zeta 3, and in the denominator it will be zeta 1 minus zeta 2 and zeta 1 minus zeta 3. So, the denominator is this, zeta 1 minus zeta 2 is minus 1 and zeta 1 minus zeta 3 is minus 2, right. So, this is equal to 1 by 2 into zeta minus zeta 2, zeta minus zeta 3, okay. And let us look at its values. So, at its value is, when zeta equals zeta 1, what does the numerator become? 1 minus 0 into 1 minus, excuse me, minus 1. So, what does its value become? It becomes 1 by 2 into minus 1 into minus 2, and this equals 1 at zeta equals minus 1. At zeta equals 0, it becomes 1 by 2 into 0 at zeta equals 0, and this is equal to 1 by 2 into 0 at zeta equals plus 1. The expression for psi 2, and that equals, in the numerator the first term will be zeta minus zeta 1 and the second term will be zeta minus zeta 3, and in the denominator it will be zeta 2 minus zeta 1 and zeta 2 minus zeta 3. and this equals minus 1 times zeta minus zeta 1, zeta minus zeta 3, and the values are 0, 1, 0. This is at zeta equals minus 1, at zeta equals 0, at zeta equals plus 1. Any questions? And likewise, the third approximation function psi 3 will be, I will directly write the results, it will be half zeta minus zeta 1, zeta minus zeta 2, and this value is 0, 0, 1 at minus 1, at 0, at plus 1. So, these are the expression for quadratic functional functions, approximation functions. These are the expressions for linear approximation functions. So, likewise, in a very systematic way and very easily, we can generate approximation functions of any order, Legendre approximation functions of Lagrangian approximation functions of any order using this equation C. So, now what we will do is we will move on to the next topic, and that is all about approximation of geometry. Okay. So, what is our final goal? Our final goal is that somehow given f x, we should be able to numerically integrate it on the domain of an actual element which varies from, which has limits x a to x b. We want to integrate it, because when we have to construct stiffness matrix or K matrix K I j or f I, the force vector, we have to perform these integrations, right, and we perform these integrations over the length of an element. Now, we have seen that if I can somehow map these elements into or onto an element in the natural coordinate system, then things become easier and more systematic. So, what we have done till so far is we have developed a mapping mechanism, right. This is what we did here. We have developed a transformation mechanism to map the eth element in actual coordinate system to eth element in natural coordinate system. This is the first thing we did. The second thing is that if we are in the natural coordinate system, we should be able to easily calculate the approximation functions there. We know because if this is the coordinate system we are going to use, then because our integrals will involve lot of approximation functions, we should know how to develop those approximation functions in natural coordinate system. So, this is why we developed Lagrangian family of interpolation functions, the relation for those functions in natural coordinate system, which is this relation C. So, this is first part. So, the overall goal is to somehow integrate it in natural coordinate system, and for that the first requirement is that we should know how to generate Lagrangian polynomials in natural coordinate system. The second thing is we should know how geometry transforms, how geometry gets approximated. So, this is the second piece of the puzzle. Okay. This is the second piece of the puzzle. So, let us look at a function x is equal to function of zeta. Now, what is this function? So, this is a lower case f, it is not big F. When we were integrating, we were saying big F, so that is different than this lower f, small f. So, what does this relation do? It maps an actual element to an element in local, not local, natural coordinate system. Okay. It helps us map an actual element into a local coordinate system. For instance, if I have two nodes, first one is located at xa, second one is located at xb, this is node 1, this is node 2, and I have to map it to the zeta coordinate system. The coordinates are -1 to 1 and this is zeta coordinate system, right. This is node 1, this is node 2. Then the transformation function is f of zeta. And in this case, a linear element is mapped onto a linear element in zeta coordinate system and fx equals what? Oh, I am sorry, f zeta is xa plus he by 2 zeta. So, this is the expression we had developed earlier. This is not something new. In probably the first or second class, we had developed this mapping, right. This is the mapping we had developed. And what did we develop? That how you transform a two noded element, this is important to understand, a two noded element to a two noded element in the zeta coordinate system. If there was a three noded element, then this mapping relation would be different. It is important to understand, right, because then there would be three constants, a plus beta, b times zeta plus c zeta square, and then we will have to do three equations and we will have to calculate a, b and c. So, this mapping will be different, it is important to understand. So, that is why it is written in this case a linear element in x domain or x coordinate system is mapped onto a linear element in zeta coordinate system. And for this kind of transformation where you have two elements here, two nodes here, two nodes on the other side, linear element on both sides, this is the transformation function. It is important to understand. The other thing is here it is a straight line element and here also it is a straight line element. Okay. So, a straight line element is being mapped onto a straight line element. Now, consider this. Suppose I do not do this and I have a different type of element. Right. So, this is node 1, this is node 2, this is node 3, and now I am trying to map it in the zeta coordinate system. So, this is my x coordinate and here the nodes are located at -1, 0 and 1. This is node 1, node 2, node 3. So, then what is happening is, so I can say that x is equal to a plus b zeta plus c zeta square. So, a, b and c are unknown but constant. And how do I calculate these A, B and C? Again I see that node 1 has to map to 1 here and so on and so forth. So I get 3 relations between xa plus, I essentially get I get 3 relations, and from these 3 relations I calculate A, B and C, and then I plug this A, B and C back in this equation. I plug all these values of A, B, C back in this equation, right, and that is how I develop the domain, the mapping. Now when I do this kind of a transformation, then what is happening? See, what is happening is that here you have a straight line. So a straight line element gets mapped onto a curved line. It's mapped onto a curved line, or you can do it back and forth, because x is straight and zeta is 1 a plus bx plus cx zeta square, right. So it's like a quadratic expression. So it's a, so if you plot that x versus zeta, it won't be a straight line, right. The plot of this thing, if I plot this equation, it is a linear transform, it's a straight line, right. If on x axis I plot x and on y axis I plot zeta, I will get a straight line, right. Here if I make the same plot, this is a non-linear transformation, it is a curved line, I will get a curved line, right. So using this kind of approaches, I can also approximate curved geometries. This is important to understand. We will not do more about this, but just wanted to introduce this idea. So this is there. Now the other thing is, so this is important to understand and remember. Now the other important thing to note is that in FEA, when we want to do a finite element analysis, what do? The first step we do is that we break the domain into small elements, right. In FEA, step 1, we had discussed this in our first week. Step 1 is discretize domain into small elements, and then the second step is we assume approximation functions or interpolation functions, and these are assumed for what? For unknown variables. For instance, in a bar problem, we assume that u is unknown, right. In bar problem, u is unknown, and we assume that this unknown variable, how it varies over the length of each element, right. This is what we assume. And when we discretize this domain into small elements, so we do two things, and then we do other things. We construct assembly element equations, assembly equations, impose the boundary conditions and solve the equation, all that stuff we do, but these are the first two things, okay. These are the first two things. But when we are doing this, first thing is we are discretizing the domain into small elements, and the second thing is we are doing for unknown, so this is an approximation, right. This is an approximation. Why is it an approximation? If I have this kind of a domain, I can break it up into triangles, right. each of these triangles could be an element. When I discretize a mesh, right, when I discretize a geometry, each of these triangles could be an element. And this is the extra stuff which in this mesh I could not capture. This is the extra stuff. So, when we discretize, now this problem does not happen if I have a straight line. If this is our domain, 1D domain, this is 1D domain, this is 2D domain, right. So, in 1D domain, if I break this up into smaller elements, there is no problem, right. The finite element discretization of the domain is exact, there is no error introduced because of discretization. But here when I am breaking it up into small triangles or rectangles in 2D domains, I may have these green areas which are not captured in the actual thing, right. So, in finite element analysis, we not only develop approximation functions for unknown variables, but we also develop approximation functions for geometry. We also develop approximation functions for geometry, right. So, you get introduction of error here and also approximation functions when we develop for geometry, you get error, introduction of error here also, right. This is what we had discussed earlier also. So, approximation of geometry at least in 1D domain, how does it look like? That x is equal to xi e times psi I zeta I is equal to 1 to m. This is approximation of geometry. Now, in straight line it will not create a problem, but in triangles and things like that, this approximation geometry may generate some errors. So, this is approximation of geometry. So, what we will do is we will continue this discussion about approximation geometry in the next class also, and then we will start introducing things like Jacobian and stuff like that, Jacobian transformation and related things, because all these concepts will eventually help us perform the ultimate goal which is to do numerical integration using Gauss-Legendre scheme or Gauss-Legendre quadrature method. That is what our goal is. So, thanks, and we will meet tomorrow.